I'm in Australia investigating how the once teeming Fitzroy River now appears to be empty of big fish. And I've discovered there could be an unusual cause: poisonous cane toads.
Australia has fought a decades-long battle against 200 million toxic cane toads.
Controlling one of Australia's worst invasive species may involve genetically engineered cannibal toad.
In 2025, scientists tried something unprecedented. They genetically modified tadpoles to never grow up, programming them to stay in their cannibalistic larval stage forever, then released millions into the wild. These Peter Pan tadpoles targeted one thing: their own species' eggs. The result? 98% of cane toad eggs were wiped out in trial ponds.
The genetically modified animals consume up to 3 times more eggs than normal tadpoles.
But this victory raised an unsettling question. Had Australia just replaced one biological disaster with another? Let's break it down. First, let's start with how a single gamble in 1935 unleashed the invader that turned Australia's wetlands into a decades-long nightmare. The biobomb that started it all. Before anyone thought of breeding cannibal tadpoles, Australia was already trapped in a nightmare of its own making. A squat, warty toad that could kill almost anything that tried to eat it. Decades before the tadpole experiment, this single mistake had set the stage for one of the most destructive wildlife invasions in modern history. In June 1935, Queensland's sugar industry was desperate. Cane beetles were chewing through stalks, ruining harvests, and threatening to gut the economy. Spraying poisons only killed other wildlife, so officials gambled on a natural predator they had heard about from Puerto Rico and Hawaii: the cane toad, a ground-dwelling amphibian with a huge appetite. They believed it would hunt the beetles at the base of the plants. A government entomologist, McTaggart, sailed to Hawaii and returned with 102 adult toads. By August, they were breeding in outdoor pens near cairns. Within months, more than 2,400 young toads were packed up and shipped to infested fields. The beetles fed high in the stalks. The toads stayed on the ground. The plan failed immediately. Instead of climbing, the toads turned to easy prey like native insects, frogs, small reptiles, and even tiny mammals. They had no natural predators in Australia, and the females could lay as many as 30,000 eggs twice a year. Every pond and roadside ditch became a nursery. Black clouds of tadpoles clogged the water. By the late 1940s, reports of the toads came from miles beyond the first release sites, and the numbers reached tens of millions. By the 1950s, they were officially labeled a pest, but the effort to stop them was far too late. They kept spreading, sometimes floating downstream, or hitching rides on trucks. By the 2000s, they were racing across the Northern Territory at 40 kilometers a year, overrunning wetlands and pushing westward into new frontiers. Today, their population is estimated at over 200 million in Australia. But the real horror wasn't just their numbers. That horror would soon reveal itself in ways few expected. Not in the rush of an advancing horde, but in the silence that followed. What began as a cure was quietly becoming a test of control, one that nature had never agreed to. The poison that turned the wild silent. Australia's rivers, swamps, and grasslands went quiet. Freshwater crocodiles collapsed first. After cane toads arrived, their numbers dropped up to 90% in some regions. All it took was one bite. The cane toad's shoulder glands contain bufatoxins, a cocktail of compounds that cause rapid heart failure. A crocodile would lunge at what looked like an easy snack, and as soon as the toad's shoulder glands were squeezed, they released the bufatoxin that shut the predator's heart down. The crocodile would thrash, drool, seize, then go still in minutes. The same story played out across the food chain. Goannas, Australia's powerful monitor lizards, snapped up toads and died by the end of the day. Quails pecking at tadpoles vanished in whole flocks.
35,000.
So what we're looking at here, all these tadpoles are probably the product of one lady.
Death adders and other snakes, mistaking toads for frogs, died bloated. Birds such as black-faced cuckoos and butcher birds fed their chicks tainted hatchlings and lost their broods. Even small mammals like water rats dropped after a single bite. The losses didn't end with predators dying outright. Toads consumed insects, spiders, and crustaceans that native species relied on. Ponds choked with their eggs and tadpoles, robbing oxygen and space from local frogs and fish. As native predators fell, some prey species surged unchecked, then crashed when the balance collapsed. Once abundant small mammals disappeared from landscapes they had dominated for millennia. Australians tried to fight back. Volunteers turned out at night for toad-busting events, using nets and clubs under floodlights. Barriers and traps lined roads. Scientists experimented with parasites, viruses, and even trained some predators by feeding them tiny, non-lethal doses of toad toxin so they would learn to avoid the invader. Nothing worked at scale. The toads kept advancing. Then, during routine water surveys, biologist Rick Shine's team at Macquarie University saw something strange. In ponds thick with toad spawn, not all the tadpoles were just feeding. What they witnessed in those murky shallows was more than strange. It was a glimpse of a secret war already raging beneath the water's surface. A war in which the toad's own young were the executioners, the cannibal instinct that changed the war. Scientists thought the war against the cane toads would be won above the waterline by hunting the toxic adults, but the real killer was hiding beneath the surface all along. In the murky ponds, the toad's own young were devouring the next generation before it could even hatch. And that brutal instinct would soon become the most unexpected weapon in the entire fight. In northern Queensland during the wet season, a female cane toad slips into a shallow pond and releases up to 20,000 eggs. The jelly-like strands float for hours, each egg a potential new invader. But if older tadpoles from a previous clutch are already there, the eggs will almost never hatch. The moment the eggs release chemical signals that they are ready to develop, the older tadpoles detect them. They swarm like a black cloud, tearing through the strands and devouring the yolks and embryos. In field studies led by Rick Shine's team, as many as 99% of eggs in some ponds were wiped out within a single day. This brutal behavior isn't new. In the cane toad's native South America, cannibalism among tadpoles keeps their population balanced. But in Australia, it became far more intense. With few predators around to thin their numbers, tadpoles competed fiercely for limited food. The first to hatch had a huge advantage, eliminating younger rivals before they could grow. That meant millions of potential toads never even made it past the egg stage. The cannibalism slowed the boom, but didn't stop the invasion. Older tadpoles still grew up into adults that spread westward. That insight raised a new, radical idea. What if this instinct could be turned into a weapon? Instead of trying to block the invasion with fences, poisons, or hunting squads, scientists wondered if they could amplify the cannibalism, using the toad's own biology against them. The concept promised a self-sustaining solution. An army of tadpoles preying relentlessly on their own species. But translating that idea into action was another challenge entirely. To weaponize the instinct, researchers first had to understand what triggered it and whether it could be pushed to last longer, even stopping tadpoles from ever maturing. And so the question shifted from observation to manipulation. Could humans trap that raw cannibal instinct inside the tadpoles forever? making them permanent predators of their own kind. If you're intrigued by how far science was about to go, hit like now, because what came next would test the very limits of our willingness to reshape life itself. The birth of the never-growing predator. The turning point in the fight against the cane toad came from an unsettling idea. What if the toad's own young could be trapped in the one stage where they were most destructive, forever? The problem was that the cannibal stage was short-lived. Tadpoles usually transform into land-dwelling toads in about 3 weeks, leaving gaps that new clutches could exploit. If that transformation could be blocked, the most lethal life stage might be turned into a permanent weapon. The researchers homed in on a single control switch in the toad's biology: thyroxin, a hormone made by the thyroid gland that drives metamorphosis from tadpole to adult. For that, the team turned to CRISPR-Cas9, which works like a pair of precise molecular scissors. It lets scientists find an exact spot in an animal's DNA, cut it, and turn off a specific gene without changing the rest. In the cane toad, they used it to block the gene that tells the body to make thyroxin, the hormone that makes tadpoles grow legs and lungs. With that switch turned off, the young never grew up, staying in their powerful, hungry tadpole form indefinitely. Freshly laid eggs were injected under microscopes, then kept in tanks to hatch. The results were immediate. Instead of small, fast-growing larvae that quickly prepared to leave the water, these altered tadpoles bulked up, their bodies denser and more muscular. Without the push to mature, they stayed in the pond for months, driven by a relentless need to feed. The team nicknamed them Peter Pan Tadpoles, after the fictional boy who never grew up, but there was nothing playful about them. In early tests, they devoured cane toad egg masses 4 times faster than normal tadpoles and stayed active for 3 to 4 months, clearing one wave of eggs after another. Ponds guarded by them often ended up barren of new toads, yet they left native frog eggs alone, homing in only on the chemical cues released by their own species' eggs. Because no foreign DNA had been inserted, Australian regulators treated the altered tadpoles as gene-silenced, not fully genetically modified, and allowed controlled trials. Supporters hailed it as the most targeted strike yet against the invasion, while critics warned that any shift in behavior or mutation could turn the solution into a new threat. Later on, Macquarie's labs moved from sketches and small tanks to larger-scale trials. The question was no longer whether the idea worked in theory, but whether the new predators could hold the line in the real world's ponds. The answer would not come in the safety of the lab, but in the open wetlands, when the altered young were finally unleashed in millions, numbers too vast to control, like a living black tide. The black tide unleashed. February 2025. Western Australia's Kimberley region. Shine's team was about to release millions of Peter Pan tadpoles into the wild ponds. The lab trials have worked, but nature is unpredictable. Nobody knew for sure whether they would save the wetlands from the cane toad invasion or trigger a different kind of disaster. To bridge the gap between theory and the wild, Shine's team built fenced enclosures on floodplains in Western Australia and the Northern Territory. Each site was a carefully engineered replica of a natural pond, shallow clay basins surrounded by native grasses and trees, with aeration and water levels tuned to mimic the monsoon season. The purpose was simple: test whether the Peter Pan tadpoles would stay as focused and effective under real-world conditions. Regulators gave the project the green light under strict conditions. No tadpoles were to escape, and every trial would be closely monitored to ensure no harm to native frogs. With approval in hand, the team began breeding on a massive scale. Millions of the gene-silenced eggs were hatched in the lab and packed into temperature-controlled containers, ready to be deployed at the peak of the cane toad breeding season in February and March 2025. Release mornings were tense. Teams wearing waders opened crates at the pond edges just as dawn broke. Instead of a slow pour, the dark masses of tadpoles spread quickly into the shallows, forming black clouds that pulsed beneath the water's surface. Drones hovered overhead, cameras recorded every ripple, and sensors tracked water quality as the new predators settled in. The real test began as soon as the first wild female toads arrived, drawn in by pheromone baits. Each female laid as many as 20,000 eggs in long gelatinous strings. The moment the eggs hit the water, the chemical cues triggered a feeding frenzy. Swarms of Peter Pan tadpoles converged in seconds, churning the water into a black vortex that shredded the strands in hours, leaving only cloudy debris behind. Field data stunned the crews. In the ponds seeded with the modified tadpoles, up to 98% of the eggs were wiped out, nearly double the loss in untreated control ponds. Crocodiles lingered at the edges, and local fish moved more boldly, hinting that the usual cane toad toxins were already absent. But the victory felt uneasy. No young toads emerged that season, yet the question remained. What would happen in the long run, once millions of these engineered cannibals roamed the wetlands? The first signs came not with a roar, but with a hush that spread across the ponds. What the scientists discovered next shocked even the skeptics. The silent ponds. When Shine's crews waded into the Kimberley test ponds for their August 2025 survey, the water was still and strangely quiet. No waves of cane toadlets churned the shallows. Instead, the nets came up empty, and from the reeds came the soft calls of native frogs that had been missing for years. That became the first real clue that the wetlands were changing. Footage from underwater cameras confirmed what the nets hinted at. In pond after pond, strings of cane toad eggs had been laid and then erased within hours. Each time a female was lured in to spawn, the black swarms of Peter Pan tadpoles struck. They shredded the jelly strands before the embryos could hatch, leaving only faint, cloudy smears drifting in the water. That relentless assault broke the backbone of the invasion. Monitored sites showed an 85% drop in young toads, making it past the larval stage. Under normal conditions, tadpoles survive only 2 to 3 weeks before transforming into land-dwelling juveniles. But the altered ones persisted for nearly 4 months, patrolling the ponds long enough to wipe out multiple spawning waves. The engineered cannibals lingered in the ponds for 3 months, long enough to wipe out not just the first spawning wave, but the second as well. Even more surprising was how precise the effect proved to be. Native frogs' eggs, which share many of the same breeding pools, went untouched. The Peter Pan tadpoles locked onto only the chemical cues of cane toad eggs. With the toxic invaders collapsing, the rest of the food web shifted almost immediately. Within a single season, biodiversity indices jumped by more than 50% across monitored wetlands. Small fish populations in the ponds increased by 40% within weeks, no longer poisoned by toad tadpoles. Invertebrate counts, especially dragonfly larvae and water beetles, rose sharply, signaling healthier oxygen levels and improved water balance. Water birds like herons and egrets began nesting more successfully. Their chicks spared the usual toxic diet. Goannas and quokkas returned to feed along the pond edges without collapsing from seizures. Even freshwater crocodiles, whose nests had declined by 90% in the worst zones, started to rebound, with new clutches hatching without the lethal toxin trap. The turnaround stunned the team. Decades of expensive eradication campaigns had barely slowed the toads, yet a single gene tweak in their own young had gutted the invasion in a single breeding season. Shine called it ecological judo, flipping the toad's breeding power against itself. But the success carried a shadow. No one yet knew whether the Peter Pan tadpoles' focus on cane toad eggs would hold as conditions changed. Surveys continued. Sensors kept humming, because the silence in the ponds, however welcome, might not last forever. The silence across the ponds felt like victory, but also like a held breath. Because balance, once broken, has a way of rewriting its own rules. If this story caught you off guard, share it with a friend. They deserve to know how close scientists came to turning nature against itself. The fear of a second mistake. History raised the first alarm. At an April 2025 policy meeting in Darwin, a veteran ecologist slammed a stack of yellowed newspapers onto the table. Headlines from 1935 that once praised the cane toad as Australia's salvation. Within a decade, that solution had overrun the continent. The 1935 release, 102 breeding toads, no containment, no environmental review, no monitoring. The 2025 release, millions of non-breeding tadpoles, fenced enclosures, drone surveillance, and weekly testing. But critics asked, is the difference enough? The warning cut through the room like a blade. What if history was about to repeat itself, only this time with something far more engineered and far less predictable? As news of the Kimberley trials spread, egg wipes above 98%, toadlets nearly gone, headlines worldwide asked if a miracle tadpole had been found. But in environmental forums and academic panels, the mood was far from celebratory. Critics pointed to the original cane toad release, a foreign species let loose with almost no testing, which then bred unchecked, 30,000 eggs per female, 2 breeding seasons a year, poisoning predators, and collapsing native wildlife. Now, they warned, Australia was again betting its ecosystem on a biological intervention. What if the Peter Pan tadpoles didn't stay locked on cane toad eggs? What if they adapted or mutated, turning on native frogs already stressed by drought and habitat loss? Others feared that in a flood season, some might wash out of the trial enclosures and colonize new wetlands, or even evolve a way around the gene edit block and begin breeding. Shine's team countered with data. The engineered tadpoles could not metamorphose. Without lungs or legs, they would never leave the ponds or survive on land. Each one lived only about 3 months, enough to strip the cane toad clutches during the peak breeding windows and then die off. The project also operated under far tighter oversight than the hasty 1935 release. Trial ponds were sealed with silt barriers, watched by drones, and sampled weekly. Regulators approved the program under a gene-silenced category. No foreign DNA added, so the edit could not spread by breeding. Panels called the approach more like a scalpel than another invasive hammer. Still, the historical memory of the cane toad disaster shaped the debate. Editorials called it playing God twice, while conservationists asked whether even a contained gene drive could set a precedent for riskier edits elsewhere. Yet, as Australia hesitated, the rest of the world was watching with hungry eyes. To some, the risks seemed worth the gamble, and they were ready to borrow the weapon for their own battles. The global temptation. May 2025, video clips of Kimberley ponds, cane toad eggs vanishing under clouds of Peter Pan tadpoles, spread across news sites and research feeds. Conservation groups from multiple countries contacted Macquarie University. They wanted the same technology. For many, the question was no longer whether it worked. It was who would use it next, and for what. Conservation groups, fisheries managers, and even government agencies began to see possibilities in their own battles with invasive species. In North America, ecologists struggling with Asian carp, fast-breeding fish that clog rivers and crowd out native life, proposed a parallel tactic: tweak their larvae so they cannibalize their own kind before reaching adulthood. Reef biologists in the Florida Keys and the Caribbean eyed the same approach for lionfish, voracious reef invaders that decimate the fish that keep corals healthy. In Europe, managers of Scottish rivers asked whether a similar edit could control the aggressive rusty crayfish. Even Indonesia, long fighting its own expanding toad problem, inquired about licensing the technology. International agencies moved fast. In June, United Nations biodiversity panels debated how to oversee what some called reproductive rewiring. Costs were falling. Because Shine's method made only a minimal genetic change, shutting down the hormone switch that triggers metamorphosis, it sidestepped most GMO restrictions and became affordable for large-scale trials. For a moment, the mood tilted toward optimism. A single strategy might finally let humans turn the prolific breeding of invaders against themselves. But the speed of adoption ignited new fears. If each country began altering species on its own, who would decide where to draw the line? What if edited organisms crossed borders or evolved unforeseen traits? Commentaries in major journals asked whether humanity was drifting into designer Darwinism, reshaping ecosystems without a global safety net. Yet as demand surged, from the Great Lakes to Georgia's kudzu-choked hills, so did calls for restraint. The world now stands at a crossroads. On one side, a tool that can turn nature's fiercest breeders against themselves. On the other, the haunting chance that we may unleash something we cannot call back. What does this mean for the future of invasive species control? Not just in Australia, but across the globe? Could this become a model for the world, or a warning we've yet to fully understand? Tell us what you think in the comments section below. And if you want to be here when the next chapter unfolds, hit subscribe and stay curious. The story of what comes next is already being written. Thanks for watching. See you in the next one.